Hello, everybody. Welcome to video 4, STA 513. Let me get to where we left off the last time. So with the last time, we really got into discussing confidence intervals for the ANOVA. We also talked about using the confidence intervals to create graphics, as well as the ability to do one-sided tests. And we saw in this case here with the one-sided test, where the alternative to the mean of whichever the 4 levels below is greater than 17.2. We said the big thing here was to create a confidence interval where, in a sense, you double the alpha, right? So if our overall alpha was 0.05, we created a 90% confidence interval. Now, in 506, you discussed the one-sided test. And with the one-sided test, the big thing is you can develop a confidence interval for a one-sided test, but one of the bounds has either got to go to infinity or negative infinity. And remember, we said, in this case, the infinity you use is in the direction of the alternative. So if the alternative is greater than or equal to, you're using positive infinity as one of the bounds of the confidence interval. If the one-sided test is less than or equal to, if you have the equality in the alternative, the infinity you use there is less than is negative infinity. So remember, the infinity you always use is in the direction of the alternative. Greater than positive infinity, less than negative infinity. It all depends on the alternative. That's the big thing. That is the ultimate key point, the ultimate alternative. So think about that alliteration combination if you need to perform that one-sided test. But the real meat of chapter 17, you can kind of think of the confidence interval, the one-sided test, all that. And that was all really important that we did last time. But you could really think the real meat of chapter 17 is developing contrast, which are basically linear combinations of the cell means, a linear equation of the cell means set to 0. And that's what we want to do in video 4, is dissect the contrast. From the contrast, get into the topic that we introduced video 3, this idea of multiple comparison. And we'll really get into a couple of the different approaches for dissecting the multiple comparisons that we get there, and then power the contrast that we'll talk about. Now, in video 5, the next video, we'll jump to chapter 18. That should be a 1-chapter video where we focus on goodness of fit, which is going to run pretty parallel for the most part of what you guys did in 512. Just in the ANOVA setting rather than the regression model setting. But let's go ahead and get to dissecting the contrast, topic 1 of video 4. So in video, so this is where we left off, slide 19 of the chapter 17 notes. So right now, we're right here. The formal definition of a contrast is a comparison involving 2 or more factor means. And in fact, it includes the pairwise differences of the cell means that we either got through the mean statement, or I prefer the Ellis mean statement in SAS. And like I said to you guys before, you could use whichever software you feel you'll be using day to day. Whether it's STA, whether it's R, whether you're in RStudio, whether you're in Python, or whether you're in SAS Jump or SPSS, doesn't really matter. All of this terminology is part of the analytical framework of these models. The software you use has got to be the software that either wherever you're working is the predominant software they use, which is really important if you guys are in a in kind of a think tank environment, whether it's a pharmaceutical or a business setting. They may have things that require certain softwares where they start going through validation approaches, quality checks, and that usually involves everybody being on the same analytical platform. Or It's what software you feel most comfortable with. And as I said previously to you guys, I'm most comfortable in SAS. I use R on occasions for analyses. I find for myself, I'm more quicker on the data management end in SAS than R or STA. And R and STA, I kind of live in the same world where I'm able to use it, but I can really be a lot quicker in SAS. And all analytical packages kind of run parallel. So being good on one kind of set you up for being decent on the other. It's just a matter of what you use day to day. And for me, outside of the classroom, I use SAS on a day-to-day basis, use R on probably more like a week-to-week basis, and use STA more on a month-to-month basis. And, so it's kind of, whatever you're most into is probably what you're most comfortable with. And for me, it's SAS. But now, for us, a mathematical definition of a contrast looks like this. And with this, again, don't let the symbolism, scare you. But a linear contrast that we denote by the symbol L for linear contrast is nothing more than a summation, a linear combination of the cell means set to 0. The big thing with the linear contrast are that the cell means, or that the coefficients of the cell means sum to 0. Sum to 0. So now if we think about what we were just looking at, when we were doing the cell means, we went like this, mu1 equal to mu2. When we were looking at the Kent data. That's a linear contrast. In reality, we're most interested in this equation. Can we assess whether or not the two cell means are equal, or based on available data that there's sufficient evidence that the cell means are not equal? And the mean statement, the Ellis mean statement, this answered these questions for us. But this is a linear contrast. And I could write this as a linear contrast like this, where I go I'm going just 1 mu1 plus minus 1 mu2 equal to 0. That is the same equation. That is a linear contrast. And in fact, this linear contrast can be written this way. If we're dealing with Kent data, I won't put the symbolism for multiplication there, but I think you guys can get that. It's just really that. That's a linear contrast. It's a function, a linear function of the cell means, linear summation of the cell means set to 0, where the coefficients of each cell mean sum to 0. Now, in reality, I talk about a contrast like this. Now, are the two cell means equal, or is there sufficient evidence and data to indicate they separate? This is the mathematical formation of the linear contrast. You really think about either of these two. The coefficients sum to 0, the equation is set to 0. Now, mathematically, for us to focus on this linear contrast, we have the restriction that the coefficients sum to 0. That makes it a legitimate contrast. If the coefficients do not sum to 0, it is not a contrast. It may be a quantity that we're trying to estimate a value for, but it's not a formal contrast. Now with the contrast will have a standard error. We'll have a variance, in fact. This is showing us the estimate of the variance. It's nothing more than the mean squared error times the sum of the ratio of the coefficient squared over the cell size. With equal cell sizes, obviously it's a little easier. When we're focused on the Kent data, remember the Kent data the cell sizes are 5, 5, 4, 5. So so it's not equal cell size. But this is the basic setup of a linear contrast. So now, in this situation here, we could think of having the cell means for the 4 designs of the Kenton data, and then we got these respective coefficients. In SAS, the formation of the contrast is contrast. We put a label on a contrast. A label on a contrast separated by either single quotes or double quotes. Remember in SAS, if you start with a single quote, you end with a single quote. You start with the double, you end with double. Just be that consistent. But then we got the factor variable, the variable in our class statement, in this case, design. And then we have the coefficients for each of the cells. The first coefficient is the coefficient for design 1. The second number is the coefficient for design 2. The third number, the coefficient for design 3. And the fourth number, the coefficient for design 4. That is the formal layout of a linear contrast. Now remember, this is a legitimate contrast when those coefficients sum to 0. If they don't sum to 0, it's not a legitimate contrast. So cool. We got that out. So now let's focus on this. Suppose we want to see, is design 4 different than the average of the other 3? Or in fact, is design 4, bigger than design 3? We'll word these as basically a 2-sided test. But this is really what we're interested in. Can we show that design 4 is statistically superior to the average of the other 3? So this is one contrast we want to do. And if we think about this, we go, okay. Now if we go back here, and we call this our contrast of interest. Okay, for this one here, I'm going to write the null, this way. Let's go ahead and insert an equation. Let me go real quick here. So we go real quick here, design. So let me go ahead and get some of the symbols in play. Oops. Sorry about that with the toolbar coming down. Let me get the mu. So we got mu1, or my fault, mu4 equal to, come on, toolbar. So let me go real quick here, copy this guy. So this is the first contrast of interest that we want to look at. So we go, okay, it's kind of set up exactly what we saw before. That's the first contrast. Go back to the slides. Is the difference between design 4 and design 1 different? Then the difference, this should be actually difference. The difference between design 3 and design 2. So that's what we want to look at. So in this case here, this one, if we go here, we get back here to this guy. So I'll make this as the next equation. So that's mu4 minus u1. So the difference between design 4 and design 1, different than the difference between design 3 and design 2. So we go there, that's the second contrast. That's the second contrast of interest. And then the third is design 3 different than the average of 1 and 2. So if we go back here, this becomes our third contrast of interest. So I'll borrow this, bring this down, design 3. So these are our 3 contrasts of interest. And again, if we want to think, are these legitimate contrasts, we can go, okay, well, in this one, I'm just going to borrow some of the symbology. Remember, this is the same thing as we go here. Let me go here. Come on, get in there. And if we go real quick here, go inside here. And if I go, wish the mu would stay on top. So here's mu. Actually, I should change this real quick. So in fact, this one you guys can see is minus 1/3 Gotta wait for that thing to disappear. So if we go real quick here, so this ends up being minus 1/3 plus then we go, okay, in this case here, that's the equation of the linear contrast. I prefer this form of it rather than this form of it, but you know, if we go real quick here, oh. I think of the contrast written this way, but mathematically, this is the equation of the contrast. Notice the coefficients, they sum to 0. Actually, I should probably put 1 there. Those coefficients sum to 0. And then similarly, we can go here. Let me steal this part of the equation real quick there. Let me go here. Oops, not that. So if I go here, we can think of this part of the equation as minus 1u1. I put everything on the same side of the equation, plus 1u2 minus 1u3 plus 1u4 equal to 4. Again, this is to the right of the semicolon is the formal representation of the linear contrast. But again, like I said to you guys before, I think of this as the true form of the contrast. You know, because to me that means something. Is the on average difference between design 4 and design 1, how does that compare to the difference between design 3 and design 2? So in other words, we're comparing two deltas, two differences. And we're assuming, okay, we're assuming initially that the on average difference with design 4 and design 1 is equal to design difference between design 3 and design 2 until we have enough evidence in our data to contradict it. Then if we go to this one, let me steal this part of the equation again. Just to borrow it, just to make it a little easier with the math type. So if I go here, you know, that equation there becomes minus 1/2 mu1 minus 1/2 mu2 plus 1 u3 plus 0 u4 equal to 0. So this is the mathematical sum of the CI mu I equal to 0. But for us, communication-wise, remember, stats all about storytelling. This is truly, you know, the contrast that we're interested in about saying, okay, how does mu3 compare to the average of the other two? You know, so this is the mathematical form of the contrast that mimics that equation here. But in English, like we said, when we're talking storytelling wise, I think the circle components make the most sense when we're communicating the story about the data. So the question becomes, how do we do this in SAS? And again, we lay it out in SAS. It should be paralleled in a lot of the other software. So if we go here, I'm going to bring up the Kenton data again. Now, at the bottom, you see a whole bunch of golden code that we did previously in previous 513 classes. We're going to build it up ourselves. So I'm going to load the Kenton data set up. Let me make this num1. And we're going to do the equations. Well, let's just go ahead and load the data. So there's our 19 observations. Again, the 5, 5, 4, 5 with that one situation design 3 stores. And then we ran our ANOVA. So with our ANOVA, we got, okay, we saw, wow, the variance between the cell means is 18 times bigger than the average variance within the cells, indicating the on average cell means are significantly separating. We had this layout, which gave us the parameterization of the model in SAS, with 27.2 being the on average mean for the reference group, which is design 4, and then the respective deviations in the reference group. So now, let me do one thing really quick. So I'm going to go RTS, RTF file equals, let me go ahead and, oops, and throw this into the mix. I'm going to take the output to an RTF file. And we get the nums on. So now I'm going to go ahead and just run our basic ANOVA. We haven't done anything else. Now remember, the solutions will give me the regression coefficients. Without the solution, I'll just get the ANOVA table. The solutions work well and tells us, how levels are different from the reference cell. The CL parm will give us confidence limits of those parameters. But the important thing is the solution is going to tell us how SAS is parameterizing the model. So now I'm going to go ahead and run this really quick. Again, we already got, we already know what's going on with the output. So I'm going to bring this out of Word. I'm going to take it to our table right there. Right. So in this case here, oops, no, go right here. Okay, so here's our parameterization real quick. So now we see the parameterization SAS is doing, and the CL parm is giving us confidence intervals for the regression coefficients. And we see now, so right now, based on this, we know design 4 has an on average cases sold of 27.2, and we're 95% confident the true on average cases sold for design 4 of the Kenton data is between 24.10 to 30.30 cases sold on average. And then these represent the respective deviations from the reference cell. So that's fine. And again, remember, in the proc line, I didn't change the alpha. I didn't change the alpha on the proc line. So when we get back to the syntax, you know, without an alpha specified on line 41, it's going to assume you want 95% confidence intervals. So now when we start going at this, now we have the Ellis means, which gives us the cell means. But one thing that is really extremely helpful in deriving contrast is to first start with the estimated means per cell. Now line 45, or 44, my fault, will give us the estimated cell means through the Ellis mean statement. But I find if we estimate the means, quote, manually, that it will help us derive these contrasts. So in this case, I'm going to show you guys how to do that. The contrast statement forms what we call, so if I jump back here, let's see where I am. So the contrast statement performs contrast. And I know that sounds like asking a 7-year-old, you know, what the definition of thorough means. Hey, Joey, what does thorough mean? Well, thorough means, you know, we're talking about something being thorough. You know, that's what you hear a 7-year-old say. So in that one, I'm saying contrast statements perform contrast. But what I mean from contrast is that the contrast statement in SAS forms that analysis, the analysis for this statement. Well, so that's what the contrast statement does. And again, it has to have the situation where the coefficient sum to 0. What we want to do next is what we call an estimate statement. Forms estimated on average values as a function of the regression coefficients. And the regression coefficients, I mean in this table. So for us to do this, we're going to go this way here. So the first thing I'm going to do is in this, I want to use the estimate statement. Now you see it's in blue. Like the contrast, it's formed from it has a label with an apostrophe. I'm going to call this mu1. So for mu1, to get this estimate, I would go back to the parameterization. So for mu1, to guess the estimate for mu1, it's 1 times the intercept plus 1 times design 1, and then it doesn't involve the other 3. Well, for it not to involve the other 3, it's really 1 times the intercept plus 1 times design 1 plus 0 times design 2, the estimate for design 2, plus 0 times the estimate for design 3, plus 0 times the estimate for design 4, which is, obviously 0. So again, see, these are estimates. So in the estimate statement, when I'm in SAS and I go this way, intercept 1. You know, so SAS is going, okay, that's 1 times the regression coefficient for intercept. Then I go here, go back to SAS. I go design, 1. So SAS goes, okay, SAS realizes design has 4 coefficients. So 1 times this is what that first command says. When I go here, 0. So for SAS, that means plus 0 times the second, my apologies, 0 times the second coefficient. When I go back to SAS, 0 times the third coefficient. And then finally, when I go here, 0 times the fourth coefficient. So when I go here, SAS is doing all that. So now, if we recall, I'll put that in. That becomes our first estimated cell mean. This is not a contrast. This is an estimate. And it's not a contrast because the coefficients do not sum to 0. The big thing is in this estimate statement, we have 2 terms. We have the estimate parameter and we have the design, the design variable. The big thing for an estimate statement to be legitimate, to be what we call legitimate means estimable. The coefficients to the right of each variable have got to sum to the same value. This sums to 1. This sums to 1. So we go here and I run this. When I run this, here's my estimated value of mu1, 14.6. Now, if you guys notice, it's the exact same value we get to the LS mean statement. Why am I doing the estimate statement? Like I said, the estimate statement isn't giving us anything yet. Isn't giving us anything yet, but it's going to be a great tool when we want to start forming contrast, especially the very complicated contrast. So I go here, go, okay, cool. I'm going to do the same thing for design 2, 3, and 4. So for design 2, 3, and 4, it's going to work this way. It's still 1 times the intercept, but for design 2, I use the second coefficient. Design 3, the third coefficient. Design 4, the fourth coefficient of design. So again, we focus on design 3. I go back here to Word. So for design 3, it's 1 times the intercept, plus 0 times the coefficient for design 1, plus 0 times the coefficient for design 2, plus 1 times the coefficient for design 3, plus 0 times the coefficient for design 4. So remember, for our categorical variable design, we have 4 levels. So SAS is going to give us 4 corresponding parameters. And the 4 corresponding parameters represent the tau, remember the cell, the cell mean or the factor level model, where the taus represent the deviation for the respective level from the reference cell. So when we go here, this gives us the estimated means for each of the other 3 designs. This is the deviation from the reference cell for design 2, for design 3, and with design 4, it is the reference cell. We know the coefficient in the SAS parameterization 0 for the 4th cell. When we go here, I'm just going to comment out the ODS since we don't need it anymore. So when I go here, I can see my mu's 1, 2, 3, 4, 14, 6, 13, 4, 19, 5, 27.2. They replicate exactly what I got in the LS mean statement. So the LS mean statement gives us the estimated cell means. The estimate statement does as well. But the cool thing about the estimate statements is how it's going to help us form these contrasts. With contrast, we're going to do them out of order from the ones laid out on that slide. And what we're going to do them out of order is we're going to go really quick here. I'm going to call this 80B. So 80B will go right here. So 80B is this one. So the difference between design 4 and design 1 compared to the difference between design 3 and design 2. So if I go here, I'm going to go back to this one. So we'll go back to SAS. So it's mu4 minus mu1 equal to mu3 minus mu2. So that's the contrast we want to do. Now, the one thing with the SAS code, it doesn't really matter how many times you flip, how many times you reproduce the same statement. So you guys can see I'm copying the respective cell means. Now, for me, to form the left side of this equation, I'm going to go real quick here. I'm going to still call this an estimate statement, right? So I'm going to call this mu4 minus mu1. To form this estimate statement, it's actually a contrast, but to form this estimate statement, what I do is I look at these equations and I subtract the two. I subtract the two what I call coordinate-wise. So what I mean by coordinate-wise is I go to the intercept term first. 1 minus 1. This isn't high intensity math. 1 minus 1 is 0. Then I go to design. Same thing. I subtract coordinate-wise. 0 minus 1, negative 1. 0 minus 0, that's coordinate-wise, the second column, 0. 0 minus 0, the third column, coordinate-wise. And then 1 minus 0, the last column. That gives me the on average estimated difference between design 4 and design 1. Now, line 55 is a contrast statement. And it's a contrast statement because of the following, right? Anytime you have a term completely followed by all zeros, and now in this case, the intercept only has one value by it. Whenever you have a term followed completely by zeros, it doesn't need to be there. If you leave it there, it's fine. SAS, your friend, will recognize that it's really not adding anything. It's really 0 times the coefficient of intercept, which doesn't really need to be there. So if you went this way and got rid of that, that's fine. You can go, okay, in this case, I'm going to go design minus 1, 0, 0, 1. That's fine. I'll call this estimate mu4 minus mu1a. That's totally fine. If a term is followed entirely by all zeros, it does not need to be in the estimate statement. If you keep it there, it's not a problem. If you take it out, it's not a problem. So it's up to you. Sometimes I keep them in there for bookkeeping, just to keep everything straight mentally, but it's totally fine if you do not. Line 56, that is a contrast. With the factor design, all the coefficients sum to 0. So in fact, this portion of the command could be written as a contrast. So let's go ahead and take a look at the output right now, real quick, just to see what we got. When we go here, we can see real quick here, okay. Now, so here's all the output, everything we've seen before. Here's the new portion of the output real quick here. This box here is the estimate statement. This box here is the contrast. See, flags contrast. So if you notice, the mu4 minus mu1, whether or not I have the intercept value there or not, gives me exactly the same thing. That we see on average, the difference between design 4 and design 1 corresponds to 12.6 cases sold on average. And we know that difference is highly, significantly different than 0. So based on available data, we see that design 4 has a statistically superior number of cases sold on average compared to design 1. And it has, we estimate, an on average 12.6 cases more sold in the respective time period compared to design 1. So we know that. So now, if you guys notice though this, whether we use this statement or the contrast, I said to you they're exactly the same, and they are. The only thing is the contrast uses an F. The estimate statement uses the T. The estimate statement also gives you the on average estimate of the contrast, if it's able to. And we can see the on average estimated difference is 12.6. Now that's part of the story. So if you're able to have the contrast as an estimate statement, that's pretty good. That's pretty good because again, allow us to say what's going on. If you guys remember from 506, the relationship between a T and an F, you know, a T, when you're dealing with a T, when you're dealing with an F, and here's the degrees of freedom. This is the degrees of freedom of the numerator of the contrast. The denominator degrees of freedom of the contrast correspond to the degrees of freedom of the error. Similarly, these T's and these T's in our estimate statement, the degrees of freedom of those T's are the degrees of freedom of the error. So these T's have a degree of freedom of 35. But if you guys remember, a T with an F with one numerator degrees of freedom, and you know the denominator degrees of freedom in this case being 35. 35, is that correct? I believe so. Oh, my fault, 15, not 35. With the denominator degrees of freedom being 15, a T squared is an F. So if we go to this 6.13, and we're rounding the T to the second decimal, so it might not be an exact match, but if I go to 6.13 squared, that gives me 37.58. So, it's a little bit of a round off error, but this T here, the 6.13 is not, that squared is nothing more than the F. And in fact, remember the T is the estimate divided by the standard error. So if I use 12.6 divided by, I use all those decimals, 2.053930, and I square that, so that gives me 6.134553246 if I'm going crazy with the decimals, and I square that, that gives me 37.63. So again, the T squared is the F, So we see that there, so that's an exact match. The only thing attractive about the contrast as an estimate statement is it gives you the magnitude of the effect when the contrast is a one numerator degree of freedom test. So now let's get back to our syntax. Let's do the same thing here. So if I do the same thing here, the estimated difference between mu3 and mu2, same thing in line 59, 60. Subtract coordinate wise. Intercept 1 minus 1, 0. Design. Subtract coordinate wise. 0 minus 0, 0. 0 minus 1, negative 1. 1 minus 0, 1, then finally 0 minus 0. That's coordinate-wise 0. Line 61 gives us the on average difference between design 3 and design 2. And if I go here, what if I got rid of the estimate, the intercept, since it's followed entirely by zeros, or only by 0 in this case? Do I get the same thing? The answer is yes. So now if I run this code, you can see the on average difference between design 3 and design 4 are exactly the same. And again, if I wrote this as a contrast statement instead of an estimate statement, you guys will see this a little more transparent. With the contrast statement, I spell that right? Typos can really mess you up here, so definitely pay attention to the log when you guys are doing this yourself. So again, remember line 63, all the coefficients sum to 0. So if I go here, if you notice, the p-value in the contrast output, the p-value and the estimate value are exactly the same. So the estimate statement and the contrast are doing exactly the same. The thing I like about the estimate statement in this case is it does give me the magnitude of the effect. That we see an on average difference of 6.1 cases sold for design 3 being superior to design 2 on average, statistically superior. But this isn't the contrast we want. We want to compare this difference to this difference. So now let's get to it. So I'm going to borrow these two lines. I'm going to borrow these two lines. I'm going to take this guy up there. I go real quick here. So here are the on average difference between 4 and 2, the on average difference between 3 and 2. So now if I go back to the Word, so now remember, in this case here, I'm looking at this on average difference compared to this on average difference. In reality, I'm looking to see, is this difference different than this difference? In fact, is this difference minus this difference statistically different than 0? So this compared to this, the way I do it as a contrast is, in this case, I can look at this difference compared to that difference. So I'm going to call this null B, since it's the second contrast. To do this contrast, it's nothing more than subtracting this line. So this line minus this line, right? So this is mu4 minus mu1 minus the difference of mu3 minus mu2. That's the contrast. To do this contrast, again, it's nothing more than subtracting coordinate-wise. 0 minus 0, 0. Design, minus 1 minus 0, minus 1. 0 minus minus 1, 1. 0 minus 1, 1 minus 0. That's the contrast. I can either do it this way. Now realize, this is a legitimate contrast. Why? Because for each term, all the coefficients sum to 0. Sums to 0. Sums to 0. So everything is legitimate. If you didn't want to do it that way, and you didn't want to have the intercepts in the value, totally fine. Like we said, you will get exactly the same thing. Again, subtract coordinate-wise. Minus 1 minus 0. 0 minus minus 1. 0 minus 1. 1 minus 0. Again, these coefficients sum to 0. Minus 1 plus 1 is 0. Plus negative 1 is negative 1. Plus 1 is 0. When I do this, well, even before I do that, this is also a contrast. So if I go here, in this case, I like the estimate statement because it's going to give us the estimated difference. In fact, we're looking at the estimated difference of differences. You know, the mu4 minus mu1 being the first delta, the first difference, mu3 minus mu2 being the second delta, and this is the difference of differences. But when we go here, let's go ahead and run this really quick. All right, so here is, right, so this is the output that we just added on. So there's mu4 minus mu1, 12.61 difference. mu3 minus mu2, 6.1 difference. This difference of differences is 6.5. Right, so we get this standard error, we get this t, we get that p-value. So based on the available data, we have sufficient evidence in our data to indicate a significant on average difference between the difference in cases sold between design 4 and design 1, which was a 12.6 difference, compared to the difference between design 3 and design 2, a 6.1 difference, and that difference of differences corresponds to the difference between design 4 and design 1 being 6.5 cases more compared to the difference between design 3 and design 2. And again, that difference is statistically significantly different, and we can see the p-value is 0.0464. The first one contained the intercept 0. The second one did not. And then the contrast is right here. But again, realize the contrast isn't giving us the story of the direction of the effect, just the significance. So in fact, the estimate statement in this case is a little bit more informative of performing the contrast than the contrast statement. Because again, we get the story of what is driving the difference. And the thing that's driving the difference is, in fact, the difference between design 4 and design 1 is more than double the difference between design 3 and design 2. Remember, design 3 and design 2 differs by 6.1. Design 4 and design 1, 12.6. It's more than double. 6.5 cases of differences on average. That does contrast B. Let's go ahead and do contrast C. Now, the first contrast is the biggest one, the most complex one, but we'll do contrast, what I call contrast C next, right? So that was our design 4. So when I'm calling contrast C, we go back to our Word document. With our Word document, contrast C is mu3 compared to the average of the first two. So in this case here, I'm going to say mu3 compared to the average of mu1 and mu2. Okay, let me go ahead and steal lines of code. So steal line 48 down, 46 and 47. Okay, first thing I'm going to do here is get the average of mu1, mu2. Well, to get the average of mu1, mu2, add the two up together, divide by 2. So for us, to add the two together and divide by 2, it's nothing more than adding coordinate-wise and divide by 2. So 1 plus 1 is 2, divided by 2 is 1. Design, same thing. 1 plus 0 divided by 2, 0.5. 0 plus 1 divided by 2, 0.5. 0 plus 0 divided by 2, 0. And then finally, 0 plus 0 divided by 2, 0. That's the average of 1 and 2. All right, so let's just go ahead and run this, and we'll take a look at the output. You can see the line of codes are getting a little more complex. Oops. Did something not, oh, my fault. I had a typo in the line of code. That's why the log's important to you. You know, I knew the output should automatically generated. So here we go. So if we go real quick here, here are the two cell means, and our average is 14 cases sold. So now let's go ahead and do the contrast. We'll copy this again. Copy this again. So now for us to do this as an estimate statement, mu3 compared to the average of the first two, that's nothing more than mu3 minus the average of the first two. I'll call this HOC. So now I go intercept. So 1 minus 1 is 0. Design, 0 minus 0.5, negative 0.5. 0 minus 0.5, negative 0.5. 1 minus 0, that's coordinate-wise. 1, 0 minus 0, coordinate-wise, that is 0. And we said, you know, for, now, line 84, this is a legitimate contrast. Why? Because the sum of all the values following each term sum to 0. Only one term to the right of the intercept, that is 0. These coefficients sum to 0. So now, like we said before, you don't need a term in the model that is followed entirely by zeros. So I can get rid of that. And in fact, like we said, this is a contrast. So now let's go ahead and take a look at this third contrast. And I know we did them out of order. So we go here. Okay. So we know mu3 is 19.5. The average of the first two is 14, corresponds to a 5.5 difference. So we see that mu3, design 3 compared to the average of the first two, is statistically significantly different. Where design 3 has on average 5.5 cases more sold compared to the average of the first two. And that on average difference is statistically significantly different. And there's our p-value. The p-value you guys see right there is the same p-value we get from the contrast statement. Again, the contrast statements are using F's. The estimate statements are using T's. The benefit of the estimate statement, it all, besides the statistical significance, gives us the direction of the effect. And not only the direction, gives us the on average difference, but also the standard error, right? I mean, our data analysis is driven by knowledge of three things: knowledge of the mean, knowledge of the variance, and knowledge of the distribution. The distribution we got underlying all of our data is at approximate normality. For us, the knowledge of the mean is this estimated difference. The knowledge of the variability is the standard error of that estimate. You know, to tell a story, to analyze data, we need to know the three things. I always think of these three things as forming a triangle, right? And we have a triangle. The thing that connects the triangle is probability. You know, the probability of this data being observed. And you know, that's the underlying story, the underlying theory, the underlying mentality of analyzing data. Cool. We got the first two taken out. Now let's go to the last one, which is actually our first one. So I'm going to call this H0A. So it's mu4 equal to the average of mu1, mu2, mu3. All right, cool. Let's go ahead and borrow the original code. I'm going to copy this all down here. And it doesn't matter how many times you reproduce code. If it's helping you mentally complete the contrast, do it. You know, this isn't, I'm going to actually save this code. I guess I'll call this remote 2020. It doesn't really matter what we're doing, you know, what you're doing. This line of code, this code does not take up a lot of space. So a lot of times, I think it's pretty cool to keep it on. Okay, so we got mu4 there. So now, let's go ahead and get the, I can type. So let's get the average of the other three. So 93, 94, 95. So in this case here, again, it's adding coordinate-wise. 1 plus 1 plus 1 divided by 3, that's the average. Add the 3 up, divide by how many you got. So now we go to design, do the same thing, adding coordinate-wise. 1 plus 0 plus 0, it's 1, divided by 3, it's 1/3. 0 plus 1 plus 0 divided by 3, that's also 1/3. If I could type, 0 plus 0 plus 1 divided by 3, also 1/3. 0 plus 0 plus 0 divided by 3, that's 0. Okay, really quick, I'm going to comment out the other statements. So we just don't have a lot of output real quick. So I'm going to comment out that block of code. So all we got is this block of code real quick as part of our output. And again, color coding of the SAS enhanced editor lets me see that I had a mistake there with that dangling apostrophe. So now I'm going to run this line of code, this block of code. Now keep an eye on the log. So when I look at the output, I don't see the contract, the estimate statements generated. I go to this, go, What's going on? SAS doesn't like 1/3. SAS is not seeing 1/3 as an entry. All right, it just doesn't like it. So SAS doesn't like fractions, you know, where I'm writing the mathematical fraction with the slash. So I got to turn these guys into decimals. So let's go here. Okay, so we knew this was messed up. SAS doesn't like fractions. So, okay, let's go here. Average, mu1, mu2, mu3, if I could type. Okay, so we do the same thing. Actually, I'd also messed that mistake there as well. Intercept, so now I'm gonna go here. Design. Let's go ahead and leave it like that. You know, so okay, 1/3, just make it 0.33. Okay, so let's go ahead and run this. No estimate statement here. SAS didn't run the estimate statement. I go here, I look at the log. Now remember, we had the color scheme. You know, blue good for you, red you're dead, green, what does it mean? I don't have any red, I don't have any green. The only thing I have is SAS saying to me, the average of mu1, mu2, mu3 is not estimable. If I go back to my syntax. So if I look real quick here, line 99, why is that not estimable? Duh, I don't know, yeah, I made the two mistakes. Should have been 1, right? In this case here, when I add the intercept, 1, 1, 1, adds to 3, divide by 3, it's 1. Okay, so that was my, quote, stupidity. Let's run this again. When I run this again, I go here. The estimate did not run. The estimate is not estimable. Initially, I thought it was me and my stupidity on line 99 not having the coefficient, the coefficient of the intercept correct. So this statement's not estimable. And the question is, why is it not estimable? Remember we said for an estimate statement to be estimable, to be correct, is that the sum of the terms following each variable have got to sum to the same value. The intercept sums to 1, right? These guys here don't sum to 1. They sum to 0.99. So it's kind of like, okay. That was me being dumb. Yeah. So in this case here, the coefficients for each term don't sum to the same value. Okay, I can fix this. I'll let that sum to the same value. So let me run this really quick. And if I go here and run this quick, mu1, mu2, mu3 is still not estimable, but it looked like they summed to the same value. Well, this guy's not estimable because it really is looking for one of those terms, in this case here, to really be 1, right? So the coefficients for each term, in this case, don't sum to 1, right? They should sum to 1. So in this case here, so that's messed up. I'm going to change this. So it's looking for it to sum to an integer in this case. All right, so let me change this one more time. So let me borrow this. Okay. Let me make this 1. Okay, that's 1. Yeah, everything's cool. So that sums to 1. Let's see how this guy rolls. So when I run this, still running into a problem here. So let me go ahead back to this guy really quick here. So the intercept is 1, design 0.33, 0.33, 0.34 is 0. Up, my mistake. So let me comment out these guys. Let me go ahead and do this. Let's look at our previous code really quick. So if you guys see here, SAS did do the estimate statement for me real quick here. Right? So in this case here, the first one that you guys see here, that estimate statement, SAS ran line 100. Let me run it again. So when I run it again, you guys notice the log, everything ran fine, right? The only thing here is SAS now has the estimate statements up here. So there's the estimate statement, 15.675. The problem with this is, okay, everything is to the same value. So the coefficients for each sum to the same value. Basically, we're estimating 99% of a value, not really the value. So now let's drop down to here. So let me get rid of that one. So as we saw before, let's run this now. So again, we got these lines of code and now this estimate statement. Now, if you guys look at this estimate statement's legitimate. That sums to 1, so we're getting 100%, not 99% of the value. And these sum to 1. So when I go here and run this, that's fine. That's fine, all right? That worked. That worked. So let's say it this way. That worked, period. That worked, exclamation point, right? We may be thinking either one of them, but this worked. This is with a question mark. And this worked. The answer is yes, but no. And the reason it's yes, but no is, who are we to put bigger weight on group 3? You know, by us putting 0.34, we're basically putting weightings. So we're weighting design 1, 33% in this estimate. Design 2, 33%. Design 4, 34%. Okay, let's make the weights a little bit more less noticeable. You can go that way, or actually let's throw another 3 into the mix. We can go this way if you want. And if I go this way, let's run these back to back. So we have these 2 estimate statements back to back. We could see real quick here, hey, you know, they're not the same. They're not the same. The t value switches a unit in the second decimal, and the estimates aren't the same. But we're still putting more weight on design 3. What if we flip the weights around? What if I ended up going this way? Go B, make this one a 4, and make this one a 3. Therefore, we're putting more weight on design 1. When I do this and run these back to back, again, you're seeing the estimate changes. The estimate changes if we put more weight on design 1 to design 3. And you could say, well, it doesn't change in the t, it doesn't change in the p-value. That does not matter. What matters is we're putting more weight on one of the levels compared to the other 2. And the big question is, who are we to do this? We can't do this, right? The way the contrast is stated, each group has the same weight in the formation of the estimated mean. Each weighs a third. So we have to figure out a way to make the weights the same. and not put more weight on one of the cells. Again, you could say it's barely noticeable, but the point is you may be dealing with something that's really on the border of statistical significance. However you play the weighting scheme may throw it one way or the other. And if it throws it the one way, you may be inflating your chance of making a type 1 error, of truly rejecting a correct null. And we don't want to do this. You know, the analysis says treat each, the hypothesis says treat each with the same weight. And we should do that. Now, how are we going to do that? Right? You know, so again, if we get to these, you know, so if we get to these, I'll just add this comment. So the three below work, but who are we to put more weight on one level So the answer is we can't do that. So now, this is how we're going to do it. I'm going to copy these lines of code. So get the average of these three. I'm going to put this in caps on purpose. I'm going to add the 3 columns of the intercept, 3. We'll do the same thing for design. 1 plus 0, 0, 0, 1, 0, 0, 0, 1, and then the zeros. For us to do this correctly, in this case, where you have something that really wants a fraction or the decimals don't terminate, we have a repeating decimal with a third. Line 114 is what we want. This is the correct way to do this. SAS is going to put, really divide each term by 3. So this is 3 divided by 3. That's 1. 1 divided by 3 and 1/3. 1 divided by 3 and 1/3, and 1 divided by 3 1/3. So if we do it this way, we'll call this correct. So we do it this way. There you go. There is the correct average of 1, 2, and 3. As you notice, it doesn't equal any of those. Pretty darn close when you look at the estimated mean, but it's not the same. So again, you got to do it correct. Now, the t-values, the p-values, nothing really changes dramatically, but you could be dealing with a p-value that's right on the border. And hey, you got to analyze the data correctly. And in this, the correct thing is each design has the same weight. That's cool. That's cool. We're not done yet though. So now we want to form the contrast. I'm going to bring this down. Bring this down again. Now, when we wanted to do the contrast, the way we wanted to do the contrast is before we subtracted lines. So we had the 2 estimate statements and we subtracted the lines. Well, if we want to subtract the lines, line 117 to line 114, 117, 118, well, we can't because the 1's got a divisor. Divisor equal 3. So in fact, when we want to subtract 117 from 118, we need to have a common denominator. The divisor is our denominator. So I can change this estimate statement to have the common denominator if I rewrite this like that. So again, 3 divided by 3 is 1. 3 divided by 3 is 1. Line 116 and 117 are exactly the same. Just the 1 is basically written as a fraction with the divisor 3. The thing about this, though, is with these two statements having a common denominator, this divisor 3, we can subtract coordinate-wise. So in this case here, when I go this way and form this contrast, I can go, okay, H0C, subtracting coordinate-wise, so intercept 3 minus 3, design 0 minus 1, design 0 minus, so I go 0 minus 1, so I go right here, -1, 0 minus 1, then 3 minus 0, still got the divisor equal 3. So now this creates the estimate statement, right? So again, divide by the common denominator. So now you'll notice this is a legitimate contrast. Each effect, the terms about values that follow it, sum to 0. 0 minus 1 plus minus 1 is -2, plus -1 is -3, plus 3 is 0. Again, with the intercept followed entirely by zeros, we don't need that. So I can go real quick here, get rid of this guy. Now, when I do this, and run this, this will give me mu4, the average of 1, 2, and 3. This is the on average difference and the statistical significance. So we can see design 4 has an on average 11.37 cases more sold compared to the average of the other 3 designs. And that is highly significantly different. Again, if we wanted to write this as a contrast, we can go this way. Now look at this. I'm going to use line 1. I'm going to use line 121 to form the contrast. So when I go here, you should notice that divisor is not in blue. SAS is going to have a problem with it, but let's go ahead and run it and see what SAS says in the log. So when I go here and run this, you can see real quick in the log, SAS doesn't like this. In this case here, let me go back to this. Let me get back to our word thing, right? So we go here to this first equation. Let me steal this component. All right, so if you look at this equation, that's the mathematical form of the equation. Well, for this contrast, that statement is mathematically equivalent by multiplying both sides of the equation I don't want that. There you go. Multiplying both sides of the equation. Oh, didn't want that either. And my apologies, math type sometimes a little. Is mathematically equivalent to that. Multiplying both sides of the equation by 3 gives us the bottom equation from the top. Contrast statements do not allow the divisor. So in other words, to make a legitimate contrast statement, which is mathematically equivalent to what we have in the estimate statement, we have to get rid of the fraction. We got to get rid of the denominator, the divisor. So in reality, for the contrast statement, if I go back to the syntax, this statement 122 is mathematically equivalent So statement 121, because we're just multiplying both sides of the equation by 3. The way the contrast gets around it is, remember, the contrast isn't giving us the estimated mean difference. It's just giving us the statistical significance, that 45. So whether or not, if you go to this one, so again, if I do that 11.366667 divided by the standard error 1.69441348, and then I square that ratio, that gives me 45.00, which is what you guys see in the F. So it doesn't matter if you multiply both sides of the equation. The estimate statement's good in the fact that it gives us the estimated value. So that's cool. That's cool. So we did that all by hand on the fly. And my apologies for any of my typos. Again, I'll post this on D2L for you guys to review. But we did all of these. The one we didn't do, though, is simultaneously compare 1 and 3. What this means with simultaneously compare 1 and 3, this means we want to test this at the same time we test this. So is design 4 compared to the average of design 3, are they equal? And design 3 compared to the average of design 1, 2 equal. So in this case, this is a simultaneous contrast. It's not a multiple comparison. It's a simultaneous test. The ANOVA models we do are simultaneous tests. So in this case here, with the ANOVA model, remember we know with the ANOVA model is, mu1 equal to mu2, and mu1 equal to mu3, and mu1 equal to mu4, and mu2 equal to mu3, and mu2 equal to mu4, and mu3 equal to mu4. That's the null hypothesis of the ANOVA. It's these 1, 2, 3, 4, 5, 6 simultaneous tests. That's what that is. Now with the ANOVA, when we're doing 6 tests, the ANOVA, the degrees of freedom of the ANOVA is not 6, right? The degrees of freedom, so the degrees of freedom of the ANOVA model is the number of linearly independent I can type independent, that works. All right, so in this case here, so for us, the degrees of freedom of simultaneous is the number of linearly independent contrast. So we're going to do the same thing. So on this one, if we go back to this one, I'm going to see if I can copy this. So we're looking at this. And this. So these are the 3 we want to simultaneously test. All right, so for us to do this in SAS, the only way to do this in SAS is to do this through a contrast statement. It's no longer an estimate statement. So let me show you guys how to do this in SAS. So basically we're simul, if I could spell, I guess this should have been called A. So my apologies. I called that, yeah, this should have been called A, not C. So let me make that change to the code for you guys. So I got this. So now remember, this was the contrast statement for doing A. If I go up and grab the contrast statement for C, where is C? C's right here. Here's the contrast statement for C. So now for us to do the contrast statement for both, my apologies for horrible typing. Simultaneously, H0A and H0C. To do this, get the first contrast, copy that. So we want to test this and that. For us to do this in SAS, the N is represented by a comma. Then copy the second contrast. Add that on. So this is simultaneously testing the average of the first 3 compared to 4 and the average of the first 2 compared to 3. When I run this, you guys will see this output. This simultaneous test is a 2 degree of freedom test, right? Because we got 2 components, 2 linearly independent components, 2 linearly independent components. And you can see right there, okay, based on the available data, we have sufficient evidence in our data to indicate a highly significant difference between the average of 1, 2, and 3 compared to 4, and the average of 1 and 2 compared to 3. Now remember, this is saying at least one of those contrasts has a significant separation. We know both of them do from what we did above, but in this case, at least one of them is significantly separating. And again, like we said, think of this as being a comparison to the ANOVA model. All right, so with the ANOVA model, if I go design 1 minus 1, 0, 0, that's mu1 compared to mu2. That's mu1 compared to mu3. Mu1 compared to mu4. Two compared to 3. Two compared to 4. 3 compared to 4. So again, this is mu1 equal to mu2 and mu1 equal to mu3 and mu1 equal to mu4 and mu2 equal to mu3 and mu2 equal to mu4 and mu3 equal to mu4. That's the null of the ANOVA. This has 6 components. But remember, the degrees of freedom for the ANOVA is 3, not 6, because these lines are not linearly independent. So if I go here and I run this, and we go here, so for our contrast, the ANOVA contrast, 3 degrees of freedom, 18.59, it's exactly what we got there. So again, whether or not the contrast statements or the collection of contrast statements are linearly independent or not, we don't really need to worry about that. SAS, our friend, is going to end up telling us how many or what is the degrees of freedom of the linear independent components. Or from a mathematical perspective, it's called the rank of the contrast matrix. that we end up getting. So that, again, SAS is going to do a lot of the work for us. And again, if you think about this, if we go back to our line of code, right? So with the ANOVA, we know in this case here, if we go, you know, in this case here, you know, if you first deal with the first part as a true contrast in the mathematical form, and we do the one right below it as a true contrast, so add those two statements, left-hand side, add those, right-hand side, add those. You add these two statements together, you get mu1 minus mu2 plus mu2 minus mu3 equal to 0. And mathematically, that's it. So the mu1, mu3 comparison we see right here is not linearly independent from these two statements there. Because if we add those two statements as linear contrast, we'll get the third. So again, SAS is going to do all the work for us as far as identifying linearly independent. You know, when we start thinking about those, so again, SAS will do a lot of finding those linear independent components. That's contrast. I know we just spent about, you know, an hour and a half going through that, but that's really a big component of what we need to do to take care of business in this issue here. So that's pretty cool. And, you know, so we did 3 slides in about an hour and a half, but that's pretty cool. So now if we get back to the next topic, so we blew up, and I told you, you know, all of 513 is kind of blowing up a lot of what you guys did in 512, but now we want to go ahead and focus on the next couple components, which is dissecting multiple comparisons and then power of the contrast. So with dissecting multiple comparisons, we're going to focus this first on the estimated means, the LS means. So as you guys heard me say with the first class when we talked about the syllabus, some of the homework questions are a wrap up of the topic we talked about, but it's also set up for a little important component that the lecturer did not expose you, that the readings hinted at, that we dissect when we review the homework. So you're going to see this issue of dissecting multiple comparisons with respect to the contrast a little more with some of the assignments that we'll review on the homework review video portions of the class. But now, if we get back to this, we start getting back to this, and we start looking at, you know, whether or not the multiple comparison issues of hitting a significant finding just by accident, basically us committing a type 1 error. And when we do a number of hypothesis tests, there's a chance we hit a type 1 error by accident. And remember, we saw last week how the probability of type 1 error went up as we did multiple tests. But the big component of that topic, as we saw before, was that we were talking about linearly independent tests. Or my fault, we're talking about independent associations. And you guys see with the Savitz and Olshan line right here. Well, with these estimated means, they're not necessarily linearly independent. If we go back to here, you know, if we're focusing on the difference between the purple and the red, now we know you know, if they're significantly different, it's kind of like, shouldn't the green and the red be significantly different? It's a bigger difference. And if the sample sizes are the same, we would think that would fall out. Obviously, with Kent data, we're dealing with the 5545 issue. but the 4 is the blue, so they are the same size. So it's almost, we don't have necessarily independent associations. If this is statistically significantly different, then this should also be by following, by like riding the coattails, as they say. Because again, that's bigger. So we're in this kind of a little bit of a gray zone. The Savitson-Olshan gives the formula for independent associations. While the data is independent, we know numerically, there is this difference, and this difference is bigger. If this is significant, that should also be because of the magnitude of the effect. So, even though the data is independent, this contrast magnitudes not necessarily independent in the magnitude sense. So we got to figure out a way to kind of accommodate that issue. And for us, a lot of the approaches we talk about look at trying to embrace that fact that we just looked at. So there are 3 techniques that we're going to use for doing multiple comparison adjustments for comparing estimated mean differences between the designs, whether it's the Ellis means or the means. The 3 approaches we're going to talk about are the Tukey, the Chaffee, and the Bonferroni. These are the 3 most common multiple comparison adjustment techniques. Now, so each of them depends on sample size, but the goal is that the alpha rate for all the multiple comparisons is set at the a priori alpha level. So if the alpha level is 0.05, they call that the family of contrast. The Tukey and Chaffee really works well when you're just exploring the data, or what we call data mining. The Bonferroni is the most strict, and it really works when we start talking about, a pre-specified effect. The Tukey uses this thing called the Stuyvesant range distribution. It's this thing called the Q distribution in the textbook. If you guys look at the page 1333 in the full book, again, I've focused you guys on the portions of the book when we go through the syllabus. In SAS, this Q distribution is through this prob MC function. The Tukey tries to create this thing called the honest significant difference. So again, it tries to figure out what is the minimal difference where things are statistically significantly different. And therefore, we get that riding the coattails effect accommodated for. The Tukey approach does the derivation for us in creating this honestly significant difference based on the Q distribution, the mean squared error, and the sample size per cell. The formula requires equal ends. When we don't have equal ends, SAS uses this Tukey-Kramer approach. So let me jump you guys to this portion of the code. So I go real quick, I'll open up this multiple comparison, 16685, multiple adjustment, load the data, print the data. And again, we can do this Tukey approach in either the means line. I kind of like the Ellis means line. And again, we're going to see the Ellis means line when we adjust for covariates, like a multiple regression. And with the Ellis means line, it's just adjust equal Tukey. When I do this and run this component, let me get to the output from the beginning. Right, our overall ANOVA, so these p-values are unadjusted for multiple comparisons. Here are the cases, the means. Right, so we can go real quick here. Here's the confidence intervals for each of the cell means. Then here is the Tukey adjustment. Right, so the Tukey adjustment, SAS is going through trying to find this honestly significant difference, right? So it's giving us Q distribution value, the mean squared error, and then this is the HSD. So when anything is 6.10 or more different, it is model-based adjusted significant difference, adjusted for the multiple comparisons. So in this case here, the case is Tukey group meaning. So what you can see is when we do the multiple comparison adjustment, only design 4 is significantly different from the other 3. See, design 3 is followed in the red block. And then if we go here, so again, Tukey range, I kind of like this one a little bit more. So in this case here, you know, SAS is going, okay, comparison significant at 0.05 for the multiple comparisons. So anything with triple stars are statistically significantly different adjusted for the multiple comparisons. So all pairwise comparisons. And what you guys see is only design 4 is statistically significantly superior than the other 3 when we adjust for the multiple comparisons through the Tukey technique. So now let's keep an eye, let's focus on the 4-1 comparison. So with the 4-1 comparison, you can see in this case here, the Tukey adjusted confidence interval for the mean difference is that. So if we go here, 6.68 to 18.52. Right, so Tukey 4-1 comparison. We go, okay, this goes from 6.680 18.52. So we got that with the Tukey. That's the 4-1 comparison. Get right there. So we got that. That's cool. Doesn't matter if you do LS means or not. This is multiple comparison. All right, so it's doing the multiple comparison difference. So again, the 1-4, we can see there. See, the interesting thing is when we look at 2 compared to 3, now no longer significantly different when we do the multiple comparison with the Tukey approach. And right there. So again, right there. So that's cool. That's cool. That's the Tukey. If we do the Chaffee, and let's go ahead and define the Chaffee in the slides. All right, so we got that right there. The Chaffee is a little bit more conservative. It's based on the F from the overall model. And again, it uses the mean squared error and uses contrast. Again, SAS is doing all the mathematics for us. So it's based on the mean square between the mean squared error, and then our test statistic is going to be a function of the contrast, the standard error of the contrast, and the degrees of freedom from the original model. So that's the number of levels minus 1. So with the Chaffee, we'll do this mathematically, or SAS-wise rather. We go right here, and we go right here. Again, give us the whole top. I'll go from the beginning. Right, so again, there's the T. Here comes the Chaffee. Here's the, you know, all the information with the Chaffee. So again, the 4s are separating. But with the Chaffee, the 95% multiple adjusted confidence interval for the Chaffee ends up being 6.15 to 19.05. So we go here to the Chaffee. The Chaffee 6.641. This gives us 6.15 to 19.05. So the Tukey gives a narrower multiple adjusted confidence interval than the Chaffee. So next we're going to go to, not the Bob, that's me. We're going to go to the bond 4-1. Again, I apologize for my typos to you guys. But let's go ahead and look at the rest of the SAS output. This is from the mean statement. The means with the lines gives us this color code. You guys may be seeing letters. Again, this is from the LS means adjustment multiple comparison Chevet. Right, here's the 2-3 now, 0.0895. Right, so again, these p-values are adjusted for the multiple comparisons. Again, there's our confidence interval. This is 1 compared to 4 as opposed to 4 compared to 1. Now let's do the last approach, the Bonferroni. So the Bonferroni, when we go here with the slides, this one's basically the sledgehammer. And what the Bonferroni does, it kind of follows that Savitz and Olshan approach, which goes, okay, you know what? How many comparisons are we doing? Whatever our original alpha level is, divide by that number of comparisons and set that as our alpha level for significance, or the alpha for the T when we're creating confidence intervals. So if you got 3 comparisons, our alpha for significance is 0.017. So when we're doing the Bonferroni adjustment, SAS is going to do that ourselves. So if we go real quick here, so we don't need to adjust the alpha mentally when we do the Bonferroni. Real quick here, when I run this, so check this out. When I get to the Bonferroni, I'll go up to the top. All right, so the Bonferroni. All right, we get real quick here. It's going to be real quick there as we start getting it. So in this case here, this one doesn't have any adjustment. So the unadjusted confidence interval for 4-1, you see right there. So 8.22 to 16.978. It's the unadjusted confidence interval. And that's being asked on line 82. 82 is unadjusted. 84 and 85 are doing the adjustment through the mean statement right here. So here's the Bonferroni. The Bonferroni for 4-1 is 6.364 to 18.836. So now if we look at these visually again, all right, so if I do unadjusted, we're basically here 8.22 to 16.98 if I rounded to 2 decimals. Here's the Bonferroni. All right, 6.36 to the 18.836. So as we notice here, the unadjustment is going to give us the most narrow, but that's making no adjustments for multiple comparisons. In this example, the Tukey gives us the most narrow confidence interval. The Chevet gives us the widest. The Bonferroni's, in the middle of the two, if we want to say numerically. Unadjusted would always give us the most narrow confidence interval. It's making no adjustment for multiple comparisons. These are making adjustments for multiple comparisons. And again, if we focus back on the SAS output, right, so all these pairwise adjustments, they are, all the ones that are statistically significant, they are adjusted for all multiple comparisons in this table. Now, which in reality is 6. No, because again, 4-1, 1-4 are the same thing, just in opposite direction. So that's what we see there. Now, if you guys see here, one of the things we see as well is in this case here, if I don't I could do the Bonferroni manually myself. And line 97 is doing the Bonferroni manually, where I take the original alpha level, 0.05, divided by 6. 0.05 divided by 6 gives me this. So line 97 and line 99 in the Ellis mean statement are doing basically the same thing. Now, they're both giving me Bonferroni adjusted. So let me show you guys this. So whether you want to do it manually yourself and you divide the output by the number of comparisons, or you want SAS to do it, it's up to you. It's up to you. This is the confidence interval where I'm doing the alpha adjustment myself. And again, with the 4-1, or in this case, look at 1-4, look at that lower bound, minus 18.8364. And then when I have SAS do it, I get exactly the same thing. The difference of the outputs, this is giving us a simultaneous or multiple comparison adjustment via the Bonferroni technique. This is flagged by the confidence interval being changed, where I'm manually adjusting it. They both give you the same thing. You know, again, it's kind of an up to you. Now, there's no reason not to do them all in one block of syntax, right? Line 122, unadjusted. Line 123, Tukey adjusted. 124, Chaffee adjusted. 125, Bonferroni adjusted. You could do it in either the mean statement. I prefer the Ellis mean statement. The one thing you guys will notice is this is going to give a lot of output. And that's the only thing you have to really navigate is the amount of output you're going to get from this, right? So again, if I go to the top of this, you can see a lot of output. I'm not trying to make you dizzy. If you're getting dizzy, my apologies. Here's the output, the ANOVA. Unadjusted through the mean statement. Ellis mean statement, unadjusted. LSG means adjusted Tukey-Kramer because remember the Kent data 5545. So we have the unequal cell size. So Tukey-Kramer's going to do the Tukey adjustment for unequal cell size. Chaffee and Bonferroni. When we're adjusting for multiple comparisons, what we really want is the technique that yields the most narrow confidence intervals. The unadjusted always will, but they're not adjusting for multiple comparisons. So that's one thing to keep in mind as we move this. Again, you end up working with, changing the alpha if you want, if it's a 99%, right? So again, just keep these in mind. Again, a lot of examples of what's going on as we move forward with the multiple comparisons. So no one test is the best. If we're interested in all pairwise comparisons, the rule of thumb is Tukey is the edge of giving the most narrow confidence intervals. When the number of contrasts be estimated small, about the number, about as many as there are factors, the Bonferroni gives more narrow than the Chaffee. Again, these are rules of thumb. They're not law. The best way to see which ones are given the most narrow is to produce them and then visually inspect them. When the number of desired contrasts is at least twice the number of factors, the Chaffee will usually show wider confidence spans than Bonferroni. So again, just keep this in mind as we start moving forward. So study the output, select the method with the smallest confidence spans. No single method will produce multiple comparisons uniformly best among all methods. Now, if we wanted to derive power for contrast, let me take you guys to this program. And if we go here, and I open up this one, power for the contrast, right? So we got all of our original ANOVA that we end up doing. But now, if you guys see here, when I get down here, we did the overall, right? But if I want to find a power for comparing design 1 to design 3, I would specify this contrast command. Design 1 versus design 4, this contrast command. When I run this, this is giving me the power for each of the contrasts with those cell means and that pooled standard deviation, asking for 90% power. So I would need a sample size of 758 per group, not just group 1 and group 3, per group. All right, because again, we're having 758 observations per cell is what we're asking for, the number per group. This is for 1 versus 4. Why is this smaller? Because again, 5 to 11 is a lot smaller difference than 5 to 3. So that does that. Again, these power calculations are not adjusted for multiple comparisons. If I want to adjust for multiple comparisons, you can see the adjust is not blue. So proc power is not going to like this adjustment, as you guys see in the command. The only way to adjust for power for power of contrast for multiple comparisons is through the Bonferroni approach, right? So if I go here with those two contrasts, alpha equal 0.05 is unadjusted. That's what we just saw. If I want to adjust these for multiple comparisons, I need to manually do the alpha divided by a factor of 2. When I do this, you can see in this case here, I adjusted my power to 0.025. And then this is saying I need 895 per group, 100 per group for this contrast to be statistically significantly different. So again, with the contrast, I could do that. Now, if you notice, in this case, well, the 4, what if I make this 100? All right, so we could play around with some of the sample size issues to see if we can get around some of the power. All right, so I got 895, 895, 895, 100. This was 100 for the 4 cells for 90% power. To maintain the 1-3 contrast is statistically significant, and the 1-4 in this design, both of them have over 90% power or higher. Design 3 is not in the mix. I mean, my fault, design 2 is not in the mix. What if I set that to 100? When I do that, yeah, we get a little bit of play. Still have the 90% power with the multiple comparison adjustment. Go right there. Just looking at some of these. So again, we got the group ends there. So now we got 1-3, 1-4. What if I wanted to simultaneously test these? If I put these and separated them by a comma, check this out. Right? SAS doesn't like that, how we use the comma to indicate an AND command. SAS doesn't like that. So the only way to adjust for multiple comparisons is us to manually do the alpha. Again, this is what we just ran above. So again, you see the 99. Group 2 is not involved at all. So with group 2, can we just put 0 into the cell size for group 2? Answer is no. In the power calculations, SAS wants, all, sample size in all 4 cells. If we get here, Now we go to the end. This one's unadjusted. That was our N per group. So if we do the one-way ANOVA, again, the contrast, this is the sample size for those two contrast. This is the sample size without the contrast. It's going to give us the sample size for the overall ANOVA. Now, at least one of the 4 cells is separating. Now, the big thing here is the reason we had 758 for both is because mu1 compared to mu3 differs by 2. Mu1 compared to mu2 differs by 2. So when the difference is the same size, we get the same sample size. If we want to do all 3 contrasts, mu1 to mu3, mu1 to mu2, mu1 to mu4, and per group. So again, this is giving us 85 per group for the mu1 compared to mu4 contrast. So again, you can extend as many contrasts as you want. That becomes the big component. But again, with the proc contrast, we can go to that. Now, one last topic before we close this out for video 4 is what if we have something that is not really necessarily a categorical factor, but one that we can think of as quantitative. Well, if we go here, I'm going to go back to this chapter 7, our rust inhibitor data. And so if we go to the rust inhibitor data real quick here. Load that data up. We already ran the ANOVA before. And again, we just saw brand 2 really ran highest as we saw before. So that worked pretty good. We did all the plots the last time. We got the confidence intervals. Made a lot of issues with the confidence intervals last time. And this is showing some of the contrast. So again, you guys look later on at some of the contrast that we kind of mimicked with the lecture. So again, you can focus on some of that problem right there without the divisor. Some adjustments for multiple comparisons. So again, you guys may want to review the bottom proportion, which really goes through a lot of the contrast as well. Just get another refresher onto those contrasts as we move forward. And then the last issue is when we deal with something that may be not really a categorical factor, but more of something we consider quantitative. Now, so we may think about modeling this as a linear predictor or maybe even a quadratic predictor. And if we look at this, this becomes chapter 17, 762 example. So let me go ahead and load up this data. I know this video is going a little longer compared to the other ones, but let me just lay out this data real quick. So in this case, we're going through training hours. We have a series of employees, and we're looking at this product efficiency score. So here comes the training. Print the data out. So in this case here, so as you guys see the box plot, it almost kind of looks like there could be a linear trajectory with training hours with respect to productivity, right? Again, the on average effect is really being seen. The more training a person has on average, the higher efficiency they are with respect to the product. Well, maybe we can think of this not necessarily as the training hours as a categorical predictor, but what if we think of this as a continuous predictor? So in reality, do we see as we go across the estimated means, now is there this linear patterning as we go as a function of time? All right, so again, if I go here, let me just run this one more time to where we get the means. So with the means, we can see this pecking order. Well, we go from 1 hour to 4 hours, change in productivity 9.8, right, 2 to 3. So we go from 56.57 to 49.86. That's 6.7. So not exactly the, goes 9.8, 6.7. Then we go 61.43 compared to 59.57. That's a 1.8. My fault. That's a 4.86. So doesn't necessarily look like the same amount of change, 1 to 2, 2 to 3, 3 to 4. Looks like kind of maybe a little bit of a leveling off. Like, are we hitting like a curve where we're kind of getting to the top of the roller coaster? So maybe we do see this, I'm going to call it a deceleration effect as hours go on. So maybe the trajectory is not maybe hours is not a linear predictor. Maybe it's a quadratic predictor, a parabolic shape. If we go here, I'm going to create linear hours, quadratic hours real quick here. When I run this model, it's kind of, well, I got training hours and I got linear hours. Training hours categorical, linear hours continuous here. What's this model going to do for me? Well, when I look at this model here, now in this situation, we're going to focus on, the type 1 sums of squares. The type 1 sums of squares, we talked about before, we'll talk about them big time when we get into the two-way ANOVA component of the course. It shows us the statistical significance of the predictor in the order it comes in the model. So linear hours is highly significant predictor of productivity. Training hours, after adjusting for the linear component, is still significant. The type 3 shows the significance of each term in the presence of the others. And when we have categorical hours and hours, the significance of hours adjusted for categorical hours in the model, the type 3 sum of squares mess up, because categorical hours, linear hours, are, the linear hours is inside categorical hours. So in this case here, when we're model building in this sense, this is informative. This is saying to us that, the linear hour component of the model does not explain all of the variance in productivity. There is still a significant unexplained component of the variance of productivity not explained by linear hours. So now when I go to this next model, right? So this is our original model, right? And with the original model, look at the R squared. The R squared of the ANOVA model, where we're not assuming any relationship, is 94.6474. Now I'm going to fit linear hours, quadratic hours, and whatever is left over with the type 1 sums of squares. So now, again, focus on the type 1 sums of squares. The linear hour component, highly significant. The quadratic linear portion of time, highly significant. Whatever is left over of categorical time does not yield a significant portion of variance of productivity to be explained. Right? So in this case here, this is saying to us that the overall model, accounting for linear and quadratic hours, explains all of the significance of productivity. Anything left over by categorical hours is not significant. Again, everything with the model exactly the same. The R squared is the same. So now when I simplify the model to just hours and linear hours and quadratic hours, we could see in this case here, here's mine. Now we only got 2 degrees of freedom. But look at the R squared. The R squared in the ANOVA model was 94.6474% variance explained. This one's 94.6172% variance explained. So modeling productivity with linear and quadratic time as opposed to categorical time, we only lose 0.03% variance explained. Not 3%, 0.03% variance explained. Not a sufficient, not a sizable, not a significant decrease in unexplained portion of the variance of productivity. We gain a degree of freedom. So in this case here, we're really explaining a lot of the data. So this is the linear component. This is the quadratic component. With that quadratic component being negative, that's telling me we do got that deceleration effect. So again, we're, as the hours increase, on average, productivity is going to eventually hit its max and then start coming back down. Kind of almost like an oversaturation, if you will. Again, if we look at the data, graphically, when I go here, so this is showing us what's going on with the predicted value with the linear and quadratic component. So that's pretty cool when we start looking at that. So it's definitely a interesting way of showing the data. The thing that really helped us was type 1 sums of squares in this case, being order dependent. So each effect is just for the other effects that appear in the model, as opposed to type 3, which is just for all of them at the same time. So that might be a situation, what we call model building, where you're going, okay, can we, in a sense, simplify the model away from categorical predictor? This is something that you will have to discuss hand in hand with the person whose data you're managing. And that is where we are here. So that wraps up video 4. I know this one went a little longer compared to the other ones, but again, we had a lot of good information here. This sets us up for the next video, which is chapter 18, which we call goodness of fit. So again, thank you for paying attention, and I'll see you guys down the road at video 5. So thank you and have a good day.